not very good, but I guess not too bad for an open-ended question. The answer was 3. We use Ohm's law. The current, therefore, is the voltage divided by the resistance. That's 24 divided by 8. You should be able to figure that one out without using a calculator, which is 3. Today we talk about magnetism a little bit. We talk about a few devices a little bit. So we've talked already about the electricity part of this chapter. Magnetism, basically you have a force from magnetic fields which affects charges as well. But in this case, the force that's produced acts only on moving charges. We often represent the magnetic field with a B. So electric field we often use an E. And to figure out how much force each one of these applies, this one you use F is equal to Q times E. This one you use F is equal to QV times B. And it turns out that this one actually is perpendicular to the magnetic field, whereas this one is parallel to the electric field. Magnetic fields, they're produced by moving charges as well. And this is true also of a permanent magnet, like a bar magnet or a horseshoe magnet. But the moving charges tend to be sort of localized in a sense. You usually have like what's called a surface current. You have what's called a bulk current, and that's what produces the fields. With a bar magnet, the fields that get produced look like this. So let's draw our bar magnet. Instead of having a plus and a minus, it has magnetic poles. So there could be a south pole and a north pole. And the fields basically come out of the north pole side and go into the south pole side. So your field lines would basically end up looking something like this. As with electric fields, the lines do not cross each other. You may have noticed, by the way, that I drew it with the south side up. It turns out that the Earth itself produces a magnetic field, and the magnetic field looks very much like the field produced by a bar magnet. So here's the Earth with a bar magnet drawn inside of it. Down here is Australia, and up here would be like the North Pole, South Pole, etc. Can't draw the continents. So you'll notice that I put the South Pole of the magnet at the North Pole of the Earth. That's correct. Why is the South Pole of the magnet at the North Pole of the Earth? Well, it turns out that the North Pole of the Earth is the area that the North Pole of a regular magnet will point to. So if you take a regular bar magnet, you put it on a string so that it's hanging and it can twist and turn whichever way it wants, it will try to orient so that the north pole of the bar magnet points to the geographic north for the Earth, which is the south pole of the Earth's magnetic field. So the magnet of the Earth is backwards from what we call north and south pole of the Earth. Turns out that there's another little difference, by the way, between the Earth's north and south pole, geographically speaking, and the north and south pole of the magnet. This is what's called magnetic declination. It turns out that this magnet is actually oriented more like this. So here's your north and south pole axis of rotation. Here's the actual south and north poles of the magnet. It means the magnet itself sort of spins around like this as the Earth spins. This magnet, by the way, over time actually rotates, albeit very slowly, like millions of years. So millions and millions of years in the future, the magnetic north pole may actually be at the geographic north pole. The general rule of magnets, by the way, for like a bar magnet or horseshoe magnet, that kind of thing, is similar to the law of charges. This one's called the law of poles. So law of charges says opposite charges attract, like charges repel. The law of poles says the same thing, but replace the word charge with the word pole. So the south pole of one magnet and the north pole of another magnet will attract to each other. But south pole will repel from each other. Here's maybe a slightly nicer picture of the magnetic field lines. What it's showing here is a compass that's placed everywhere around a bar magnet, because you can use a compass to map the direction of the magnetic field lines. You need something a little fancier than a compass in order to figure out how strong the magnetic field lines are, or in other words, how strong the magnetic field is in a given location. You actually need what's called a Hall probe, and basically makes use of the fact that you can tune the voltage of the Hall probe so that an electron that passes through that region or other charged particle does not deflect. And if it doesn't deflect, then you have some balance between E field and B field, and from that you can figure out what the B field strength is. So, in general, sources of magnetism are moving charges. On a microscopic level, you might have little magnetic domains in which the motion of the charges locally is aligned in a particular direction and therefore acts like a magnet. So, if all of those domains are lined up within a material, then the material is called magnetized and it has its own magnetic field. That's basically what a bar magnet is doing. How do you produce a magnetic field without having a solid magnet? Well, you run current through a wire. If you take, well, depending on how well shielded it is, you could even take like a cord that you plug into the wall. And if you move a compass near the cord, it may deflect because of the magnetic field from the cord. But basically, if you have a wire that carries current, then the magnetic field lines will be little loops around that wire. So here it is looking at it from the side. From the end, you have the current coming out of the board at you. Then the magnetic field lines will look like this. In other words, they're closed lines that make concentric circles. And actually, if we're being really particular, if the density of the lines tells you how strong the field is, it turns out that it falls off like 1 over r. So as you get farther away from the wire, the field gets weaker. So what's the unit for a magnetic field? Does anybody know offhand what the unit is? In the case of electric field, the electric field has units of volts per meter or newtons per coulomb. Those are equivalent units. For a magnetic field, the SI unit has a name. It's called Tesla. Or if you want to use a different set of units, sometimes it's given in Gauss. Why would we want to use Gauss instead of Tesla? So Tesla is the MKS standard. It means you put everything into meters, kilograms, seconds. Energy is going to be in joules. Force will be in newtons, etc. Gauss, the units will not line up like that. It's more like a CGS unit. With that said, Gauss is actually a nice, useful unit because the Earth's magnetic field is about a half a Gauss. Here it's about a half a Gauss. In Tesla, that means 5 times 10 to the minus 5 Tesla. So it's a very small number. How much magnetic field is produced by a current carrying wire? You may be wondering. It turns out that the B field strength for the wire is given by some quantity, 4 pi times 10 to the minus 7, times the current, which is enclosed by the wire, carried by the wire, divided by the distance away from the wire, times actually 2 pi. So you can cancel some numbers. All right, and if this is in amps and this is in meters, this will be in Teslas. So how far away from a wire do you have to be before a compass will deflect due to the wire more than due to the Earth's magnetic field? Well, it depends upon how much current the wire carries. Maybe you have a wire that carries 1 amp of current. Okay. Where is B equal to 0.5 Gauss? How far away? So the answer is, we solve this one for distance. D is equal to B divided by 2 times 10 to the negative 7. Whoops, sorry, got it backwards. So 2 times 10 to the negative 7 times I, and that would be in meters. Tesla meters per amp, for what it's worth. So we do a little bit of division. 2 over 5 is 0.4. That's 4 times 10 to the minus 1. So we end up with 4 times 10 to the minus 3. That's 4 millimeters. So if you have a wire that carries 1 amp of current, and you hold the compass, your compass, closer than 4 millimeters away, the compass will deflect because of the wire and the current rather than because of the earth. It will stop pointing to its magnetic north to the earth. And that's basically, that's it for magnetization as such. Electromagnets, basically what you do is you take this wire and instead of running it as a straight line, you coil it around a metal core, usually iron, which is highly magnetizable. And what will happen is it will produce a magnetic field that looks the same, but maybe is a bit stronger than the magnetic field for a bar magnet. So you just run current through it and it produces a magnetic field. You can pick up iron filings or whatever. And the stronger the field that you want, the more current that you want through it. All right. Here's a nice stylized drawing, by the way, of the Earth's magnetic field with the magnet inside of the Earth, more or less. It even shows what direction the effective current is. Why is there an effective current inside the Earth, by the way? Does anybody know? Why is there a current inside the Earth? The answer is because the core of the Earth is, or the outer core at least, is molten iron. Molten iron can flow. There are some charges present in that molten iron. So as it flows around, those charges also flow around. That produces current. That's what produces the magnetic field. It turns out that it happens to be flowing at this moment in a direction that's not entirely just east-west or west-east. It's kind of declined slightly, and so your fields are declined slightly from north and south. For what it's worth, this one shows a little map of magnetic declination. So if you're on this blue line, for example, magnetic declination is 20 degrees east. Means you have an angle between actual magnetic north and what your compass says is magnetic north, which is about 20 degrees off. And if you look closely at this map, we're about here. We're pretty close to the 0 degree declination. So compasses are actually pretty good here. You might be off by like a 1 or 2 degrees in Troy. It's not too bad. If you move to Washington or to California, then maybe you have 15 or 20 degrees off. It means if you look at your compass and it says due north, you're actually 15 degrees off from due north. You're heading 15 degrees east of north, as it turns out. As far as force on a moving charge goes, to come back to our equation, F equals QV cross B, the force is always perpendicular to both the direction that the charge moves and the direction of the field lines. So what this drawing right here is showing is you have an electron. It's initially going in between a pair of bar magnets. You have a north and you have a south. And it's going this way. So your field lines here in this diagram are like this. The electron's like this. The force that's being applied to it ends up being out of the board towards you. So what this electron will do is as it gets into where the bar magnet is, it'll start to turn. And depending on how strong the field is, it can deflect off even perpendicular or even get trapped and do this kind of a motion. It turns out, for what it's worth, that this happens with the Earth's magnetic fields, for example. Is charged particles from the solar wind interact with the Earth's magnetic field. They basically get trapped in it. And it turns out that the field is strongest near the poles and then weaker near the equator. You can see that from the field line drawing that was shown a few pages back. Oops, this one. What this basically means is that your trapped particles, when they move towards the North Pole or the South Pole, tend to be confined to a smaller space than they do out here near the equator. So what happens as a result of their being trapped in a smaller space? It means that there's more collisions between these charged particles and the molecules of the air, for example. And each time that you have a collision, if the trapped particle is high enough energy, it can knock an electron loose from a molecule in the air. And then basically what happens is that electron recombines with the molecule of the air and it emits a photon. So this is happening basically everywhere in the atmosphere, but it's happening a whole lot more frequently near the two poles. That means a whole lot more photons are being emitted near the poles. How can we observe that? Is this something that we can actually see? The answer is yes. You've all, I hope, heard of the northern and the southern lights before. The aurora borealis, for example, the northern lights. This is what causes the northern lights and the southern lights. Near the two equators, you have a lot more frequent collisions with the charged particles because they're confined more tightly due to the stronger magnetic field. And because there are more collisions, that means more photons are emitted. And because there's more photons emitted, it means you actually see light from this. And that's what causes the northern lights. All right. So, to finish today's lecture, there are 3 devices that I want to talk about. And all 3 of them make use of magnetic fields. The 3 devices that I want to talk about are the motor, the generator, and the transformer. Okay, what do these things do? The motors work, literally, by converting electrical energy into mechanical energy. In other words, they take current in the presence of a magnetic field and they use it to do work. They literally work. How do they do that? How does a motor operate? How does it function? Basically, the operation is as follows. you have, for simplicity, a loop like this that carries current around it. You place this in the presence of a magnetic field. Maybe the magnetic field is due to a pair of bar magnets. One is inside the board and one is outside the board. So you have field lines running in or out of the board. Well, each one of these wires carrying current gets some amount of force on it. The force is perpendicular to the two magnets. So if they're oriented like this, that basically means you're going to have a force this way, you're going to have a force this way, this way, this way. Nothing happens. There's no net force. But now imagine that this thing is oriented like this, and you've got your two magnets. That means that on one branch, say this one and this one, they're parallel to the magnetic field. No force. The other two are still perpendicular, but now you get a force on one of them that points this way, and on the other one it points this way. So the net amount of force is still zero, but there is a net torque. If there's a net torque, then this thing is going to want to rotate. So basically, this loop will start to spin because it's carrying current. And if you have a spinning loop like this, you can attach it to some gear cranks or like a cam and cause it to do work for you. That's basically all a motor is doing. Now there's one little thing, which is that if you just have a loop like this, then it's not going to want to spin around and around like this. It's actually going to want to do one of these. In other words, oscillate back and forth. So there's one other thing that they have to do, which is that they usually have a pair of brushes here that make contact. And one of them is connected essentially to the minus, the other essentially to the plus part of your battery. Okay, what that does is it ensures that when the loop flips to here and should otherwise stop and go back, it means that the two leads flip which side of the battery they're connected to. And so instead of flipping to here and stopping and then flipping back, you flip to here and now you've flipped contacts, and that means that you get an additional torque, so it just keeps spinning. And so what happens is during some parts of the spin you have more torque and some parts you have less torque. But you always have torque in the same direction, so it spins and spins and spins and spins. You can actually make a simple motor for yourself at home. It's actually quite simple to do. It takes a little more time than I would want to do in class. But all you need is a pair of paper clips, a copper conducting wire, which has insulation that can be scraped, a battery, like a AAA or AA battery works, and a magnet. And basically what you do is you loop the wire like this. You take the paper clips like this. You hook them onto your battery, like so. And what you do is you take these two wires, and they have some insulation material like this that goes around them. You take like a file, like a nail file might work, or a rasp would work, and you rub it back and forth until you've rasped off some of the insulation like this. And then you take your magnet, your bar magnet, put it down here like this, You might have to set it in motion initially for you, but once you set it in motion, it'll spin itself. And it'll just keep spinning itself until you drain the battery. And that's a simple motor. A generator basically does the same thing, but in reverse. So here's your DC motor. Shows the contact brushes here and here, and shows the two wires that can contact. A generator basically does the same thing in reverse. It takes mechanical energy and it converts it to electrical energy, or to current. The way that that works is that we use what's called electromagnetic induction. Another thing you can do. If you take a bar magnet and you take a coiled wire, and you move the bar magnet near the coiled wire, it induces a voltage, and hence a current in the wire. And the reason why it does that, it turns out, is because you're changing a property called magnetic flux. It's basically how strong is the magnetic field times how big around is the coil times what's the relative orientation between the two. So in order to make a generator, you basically do something like this, and you could, if you wanted to, literally do something like this. Is take a magnet, hook it up to a spring, pull it down, and let it bounce up and down inside of a coil. And that will create an electrical current. It actually gives you an AC current. Is it the best way to go for that? No. It turns out that the easier way would be to take this wire and rotate it end over end in the presence of a magnetic field. And that will also produce an AC current for you. And that's actually how most power generation actually works. Like if you go to a nuclear plant, you go to a coal plant, you go to a hydroelectric plant, you go to a wind farm, all of these things are fundamentally doing the same thing. They're using some sort of mechanical energy or thermal energy to rotate a coil in the presence of a magnetic field, and that is what produces your electrical power output. In the case of a wind, it's easiest to see. There's the propellers. The wind blows the propellers, spins the propellers. Those are then attached to a coil which spins with the propellers in between a pair of magnets, and that produces a current. Okay, the last device to talk about, and here's a diagram, by the way, of an AC generator. Again, you have to end up using some sort of brushes to make contact with the two wires, but in this case, the brushes typically are complete closed loops, and one wire contacts one and the other contacts the other. So you end up getting an AC current, as it turns out. Transformers, the last piece, the last device, basically do this. You have a pair of coiled wires next to each other, and you run an AC current through one of the two wires, say this one, your primary. And because it's an AC current, that means that you get an AC, sort of like an AC magnetic field. It's an alternating magnetic field. The magnitude or strength of the field and even the direction changes with time. Your secondary coil then detects the changing magnetic field. Does the same thing, by the way, as what happens when you take one of these guys and move it closer or farther away from the coil. So you induce some sort of a current in it, you induce some sort of a voltage in it. It turns out that there's two basic forms of transformer. One of them is called a step-up transformer. And what it does is it steps the voltage up. The way that it does that is that if you have more windings on this coil than on this coil, you'll get more voltage out. In fact, the relationship is that in over V out, the voltage, is the number of windings on the primary or input divided by the number of windings on the secondary or output. All right, so you step up the voltage. It turns out that when you do this, you step down the current. In fact, the current ratio is opposite, or is inverted from, the voltage ratio. So why do we use this? Well, basically what happens is power loss in your power lines is proportional to the amount of current present. Turns out that the power loss is determined by I squared R, the current squared times the resistance of the line. The resistance is a set quantity. It basically is determined by how big around is your power line, and how long is your power line, and what is it made out of, and how hot is it on that day, as it turns out. So what we do is we step up the voltage, at the power plant. So you start off with maybe 24,000 volts generated at the power plant. You step it up to 200,000 volts. And then you send that very long distance. Because you've reduced the current by a factor of 10, you've also reduced your loss by a factor of 100. You send that over long distance, and then you find an area substation. There's one across from campus, kind of by the middle school. There's also one kind of in one of the neighborhoods by 231. And that steps it down to about 100,000 volts, which is what's run in the overhead lines. Then you run it to the transformer box that you actually see, or the transformer cylinder that you actually see on your power line. That steps it down to your 120 volts for your house. And so this reduces the amount of power that's lost in sending current all over the country from the power station. So I think we're out of time for today. There's a few examples in the online video that you may want to go through.